Welcome back for some more reinforced concrete design. In this session, we will take a deeper look at slabs, focusing on how we design, detail, and check slabs according to the Eurocode. Reinforced concrete slabs are used as floors, roofs, and walls in building and as decks of bridges. The slabs can be divided into solid flat or rib slabs cast in situ and slabs precast in a plant. Depending on the dimensions, slabs are designed as working in one or two directions. Slabs work mostly in bending and usually have low shear stress, and therefore compression and shear reinforcement are seldom required. Slabs can be considered as wide, shallow beams with a breadth larger than 5 times the depth. A slab with a span longer than 2 widths is considered as a one-way span. The design of slabs is based on a 1 meter wide strip on simple supports. The design of continuous slabs with roughly similar spans can be based on the use of standard factors. Flat slabs are supported directly by columns and therefore divided in design into strips passing over columns and between columns. We won't be covering the design of flat slabs. Continuous slabs are designed to withstand the most unfavourable arrangement of design loads. Continuous slabs subjected predominantly to uniformly distributed loads can be designed using the following loading arrangements. The first arrangement includes that every odd span carries the maximum design permanent and variable loads, and every even span carries the maximum design permanent load. The second loading arrangement is that all spans carry the maximum design permanent and variable loads. When global elastic analysis is used, calculated moments can be redistributed by up to 30%. In certain conditions, one-way spanning continuous slabs can be analysed with a full load, so the maximum design permanent and variable loads on all spans. These conditions include mostly uniform loading, the variable load smaller than 1.25 times the permanent load, and smaller than 5 kilonewtons per meter square, roughly similar spans. The maximum moments and shear forces in such slabs can be found as factored full load F times L, that is, the full load times the span length, applied on a typical span. The corresponding reduction coefficients depend on the type of slab end support and are summarised in the table on this slide. The first step in slab design using coefficients is to determine the condition of the end support. The end support of the slab is considered as simple when the slab end rests on a block work wall, or considered monolithic when the slab end is framed into a reinforced concrete wall. Next, the full load and moment are calculated for a 1 meter wide strip of the slab, where the full load F is fully factored, permanent and variable loads applied to the longer span of the slab. The moments and shear forces are calculated for the key positions in the slab, including end support, middle of end span, first internal support, typical middle of internal span, and typical internal support. The moments above supports can be redistributed by up to 20%. The values of the depth of the neutral axis X and of the lever arm Z are checked against the limits defining that the X to D ratio should be smaller than 0.45 and the Z to D ratio smaller than 0.95. It can be noted that a typical value of the X to D ratio equals 0.25 and a typical value for the Z to D ratio is 0.9. In the next design stage, the required area of tension reinforcement is evaluated using formulas or design charts. The reinforcement arrangement is designed for 1 meter wide strip of the slab, where the bar diameter and the spacing of bars are selected. This table gives the provided reinforcement area in 1 meter wide strips, depending on the bar diameter and spacing. Only reinforcing bars with the ductility classes B and C must be used in the design. Next, the shear capacity of the slab is checked. Shear reinforcement is usually not required in slabs loaded by uniformly distributed loads. The deflection is checked using the span to effective depth ratio. This table shows the basic values of the span to effective depth ratio calculated for different reinforcement ratios and locations within a continuous slab. The Eurocode limits the area of reinforcement in the slab in a certain range defined by the minimum and maximum values. The minimum area of reinforcement is calculated as a fraction of the cross-sectional area of the 1 meter wide strip of the slab, depending on the tensile strength of concrete and the yielding strength of steel. This table provides the values of minimum reinforcement ratios depending on concrete class. The area of reinforcement provided in the slab should be smaller than 4% of the cross-sectional area of the 1 metre wide strip of the slab. To eliminate large unreinforced zones, the maximum spacing of bars in slabs is defined for the main reinforcement as a smaller value between 3 slab depths or 400 millimeters, and for the secondary reinforcement as a smaller value between 3.5 times the slab depth or 450 millimeters. Note that the main reinforcement is placed in the working direction of the one-way slab, and the secondary reinforcement is placed in the perpendicular direction. For the areas of concentrated loads, these limits are reduced to a smaller value of between 2 slab depths or 250 millimeters for the main reinforcement and to a smaller value of between 3 slab depths or 400 millimeters for the secondary reinforcement. At a simply supported end of a slab, at least 50% of the span reinforcement should be anchored within the support, where the anchoring length is calculated based on the yielding strength of steel, the strength of bond between bar and surrounding concrete, bond conditions, and anchored bar diameter. Unsupported edges of slabs should be reinforced by U-bars with a length of at least 2 slab depths. These U-bars should be anchored by the top and bottom transverse bars. The arrangement of reinforcement in a slab is defined by curtailment rules, which depend on the number of spans the slab has and provide necessary anchorage to reinforcing bars. Eurocode 2 requires only 50% of span bottom reinforcement to continue to supports, and top reinforcement above supports should extend into the span. Here you can see the curtailment rules outlined for simply supported slab and a continuous slab. And that concludes our session on slab behaviour, analysis and detailing. Join me next time when we'll look in more detail at punching shear and how we ensure that slab column connections remain safe.